The next one is independently given, actually it is spherical coordinate system. Again, developed in the Cartesian coordinate system, like cylindrical coordinate system. Taking the basis as Cartesian coordinate system. That's why even in cylindrical coordinate system, we spoke about XZ plane and all, right? Z axis we spoke about, XZ plane we spoke about. Here also, we develop this with respect to the Cartesian coordinate system. Cylindrical coordinate system is the extension of circular coordinate system, but spherical coordinate system straight away is defined in the space itself, in three-dimensional space itself. Then here also, every point is specified as the point of intersection of three surfaces. Right? Surface 1. That gives the coordinate 1. Sphere of radius r. Having the center at origin. Now, you are able to visualize, right? I have a point in space and the three-dimensional Cartesian coordinate system with origin. The first surface is what? The spherical surface. Drawn through the point of interest. We'll have the radius equal to the distance of the point in Cartesian coordinate system from the center. Sphere of radius r having the center at origin. Let us see this also. When it is a sphere of radius r having the center at origin, only one coordinate is fixed in that r. It is drawn as a circle, but to be visualized as a sphere. Normal x, y, z axis. I'll not do this. Number 1. Surface 2 is cone of semi-vertical angle theta. Having its vertex at origin and z-axis as its axis. S2. S2 is this. Conical surface extending up till infinity with semi-vertical angle theta. Semi-vertical is that's all, from axis to the directrix, which is rotated to generate this conical surface. This is also theta. And before actually telling the other thing, the point lies, let us say, on the sphere of radius r and the cone of semi-vertical angle theta. This is theta, and we know this is r. The point now will lie on the line along which these two surfaces intersect. Please try to visualize it in space. It's a sphere. A cone is going out. When it goes out, it cuts the sphere along a circle, because it is a cone going out from the center. This is actually a cap-like surface that gets removed. Somewhere we want to talk about that also. But this cone intersects the spherical surface along a horizontal circle at z is equal to r cos theta of radius r sin theta. Very important for you to understand this. We can take any amount of time. Today we have to complete this spherical coordinate system, that's all. Try to understand this. If you want to understand this, definitely yes. It is at origin. This is going to this. This length is r. I will consider a right angle triangle like this at any point. It's a right angle triangle. What is this side? Definitely r cos theta. What is this radius? R sin theta. When we say that theta is equal to 0, that circle will have radius 0 at z is equal to r. As theta is increased, the radius of the circle will increase and it starts coming down, correct? As theta is increased, r cos theta will decrease and r sin theta will increase. As theta is increased, the circle along which they intersect will come down with its radius increasing. When you talk about this circle called as the greatest circle in this sphere, we say cone of semi-vertical angle theta is equal to pi by 2, where r cos theta will become 0 through origin. R sin theta will become equal to r. It's good to see. If theta is basically increased, I want to cover the entire sphere. I should create the circles at each and every point on the sphere by cutting it with a cone. When I vary theta from 0 to pi by 2, please see this. I would have produced all the circles in the upper hemisphere, starting from 0 radius at z to radius r at z is equal to 0. It has come down. if I increase theta measured from positive z axis, this is the cone for theta greater than pi by 2. R sin theta will decrease. Sin theta is the radius of the circle. R sin theta from maximum value will start decreasing and becomes equal to 0 when theta is equal to pi by pi. Correct? And you should know z r cos theta will start becoming negative. That means it produces the circle on negative z planes. Z is equal to minus value planes. That will increase from 0 to minus r. Now the circle will go down. Initially, the radius of the circle will increase while coming down. It still continues to go down. Increase to the maximum value equal to the radius of the sphere. Then again will continue to continuously decrease to 0. We should know that 0 is less than or equal to r less than or equal to infinity. Radius of the sphere can be any value between 0 to infinity. What is the range of values of theta? To cover the entire sphere, I need to vary theta only from 0 less than or equal to theta less than or equal to pi. Correct only, no? Theta cannot be varied beyond. The maximum value of theta to cover the entire sphere is pi. Pi by 2 is maximum. Pi by 2 will produce the greatest circle of radius, maximum radius r equal to the radius of the sphere at z is equal to 0. Till pi, if I go, it will go down by the radius also going decreasing towards 0. Sin theta is 0 at 0 and pi. You should know in antennas and wave propagation that theta can only vary from 0 to pi. If the antenna is there kept on the surface of the earth assumed to be horizontal, in the upper hemisphere, theta can only vary from 0 to pi by 2. In the problems of antennas, it is really important for us to know this. We have it. Range of values of theta. Now, having given these two surfaces containing the point of interest, now my uncertainty is only on the circle of radius or sin theta. Wherever it is, I'm not worried about it. On a circle of given radius, my uncertainty is only angle, correct? Now the other surface is what? S3. Is the same phi surface that we had in circular coordinate system. Because I want to select phi on the circle 0 to 2 pi. S3 is the plane. Vertical plane extending from z axis. And making an angle phi with xz plane. Any circle, if I have produced this particular surface, then I will basically cut it by a plane, making an angle phi, so that I will come to that particular point of interest. Check it. Same plane that we had in cylindrical coordinates, but the order is the last one. Similar to phi is equal to constant plane in cylindrical coordinates, we have the third. Because I want to select a point on the circle. Point on the circle, wherever it is, it should be phi means what? Because I should be able to produce that phi wherever it is, it should be infinite vertical plane. Because the sphere can have any radius from 0 to infinity. And it goes from minus infinity to plus infinity, because of which it should be a plane in wherever the Wherever you produce a circle of radius given r, I should be in a position to talk about different points by just giving the angle on that particular circle, which varies only from 0 to 2 pi, measured in the anti-clockwise direction, and the range is only 0 to 2 pi. Phi very small. 0 less than or equal to 5 less than or equal to 2. Check it. Now, because there are two angles, theta and phi. Earlier, one angle only was creating the trouble for us, so that we could not define the distance between 2 points straight away, because we could not define a vector from any point to any point. Only if they are there in the same phi plane. Now there are two angles because of which you should know that no unit vector will have fixed direction here. For us to know. Now, I will talk about vectors only, because talking about the distance between 2 points, vector from any 2 points is basically not there in spherical coordinate system. Any point we say, or with or theta and phi, we'll say. At this angle theta, at this phi, I have this point is what we will say. And all the distances are because they are measured from origin, because the source is always kept at origin and the analysis is carried out. R only is the distance of the point. In which direction given by theta and phi, I will say there. That's all. We don't talk about the vector from one point to the other point in this coordinate system, at least. Here we are supposed to define the unit vectors. Arrow. Arrow is what? Vectors in spherical coordinate system are of the form. Very important to know. Very important to know again. Are of the form AR, small ar, plus A theta, theta component, small a theta, plus A phi, small a phi. Definitely at each and every point, AR, A theta, A phi are mutually perpendicular unit vectors. Every unit vector is perpendicular to the other two, like AX, AY, AZ, and A rho, A phi, and AZ. Orthonormal basis vectors. Now we have to define AR. AR is what? Vector of unit magnitude perpendicular to normal AR. The sphere of constant radius at any point. At any point, sphere of constant correct enough? Radius passing through the point in the direction of increasing R. Fine. We know this. We can write this first. A theta cone of semi-vertical angle theta passing through the point in the direction of increasing theta. A phi. Plane at phi is equal to constant passing through the point in the direction of increasing phi. They are mutually perpendicular. Let us look into the unit vectors. If a sphere of radius r, I think you are sure that at any point on the sphere, radial line only is AR, correct? Wherever you go, radially outwards is AR. Listen carefully. Assuming the plane we are there into the YZ plane, this plane is phi is equal to 90 plane, correct? Phi is equal to 90 plane. Actually, this is the cone of semi-vertical angle theta. It cuts it along the horizontal circle, and from z-axis, this is the plane. To the right, very important for me. All are intersecting at this point, right? This is the point. What is AR component? This is AR because at that point it is radial. Hey, what is A theta? A theta is perpendicular to the cone at this point, which is the tangent to the sphere, correct? A theta can be considered as the tangent to the sphere. Definitely, because it is like this, perpendicular to R, one tangent to the sphere. What is Fi? Perpendicular to the plane. In the direction of increasing phi, it goes into. I will put it like this. With cross mark says A phi. AR, A theta, A phi. Into the border. At this point, AR, A theta, this is AR, this is A theta. What is this plane? 270 degrees plane, right? It has rotated about Z axis. From XZ plane, which is vertical and coming out from the board, I have rotated it by 90 to talk about YZ plane. If I rotate it is further 180 degrees, I will come to the left, and this is phi is equal to 270 degrees plane. AR is this, A theta is this. Now A phi is towards us because later on phi comes towards it. This plane comes towards me if I increase phi, because I rotate it like this. It goes into the board to the right. It comes out of the board to the left. I will show one more case. Please check it once. This actually, this A phi is what? Tangent to the circle of radius rho sin theta. Tangent to the circle of radius rho sin theta. It is a horizontal vector. Is A phi. A phi is always horizontal. AR is always radial to the sphere. A theta is always tangential to the sphere. A phi is always horizontal, and that A phi happens to be the tangent to the circle of radius or sin theta at that particular point because it is horizontal. I cannot call it as the tangent to the sphere. I should call it as the tangent to the circle of radius or sin theta produced because the sphere of radius r got intersected with the cone of semi-vertical angle theta. Please check. A phi is towards us, right? If I consider this at this particular point, in fact, it becomes very difficult for me to show. Right? I have to come to that point from the center and say this is AR, and then this is A phi. Tangent to this is, sorry, A theta is this, and then A phi is tangent to the circle like this. AR, A theta, A phi, if I am there at this point. They are mutually perpendicular, no doubt. Next. Next is what? Differential vector. In this coordinate system. Please listen. At any point with coordinates r, theta, phi, I will change r by dr without changing theta and phi. I can do that. On the same plane, on the same cone, producing dr here. Plus, listen carefully. Keeping r and phi constant, keeping r and phi constant on this circle. Now, this r and phi constant on the same plane. If theta is varied by d theta, by how much I will move in this direction along theta? This is radial direction. This is theta direction. This is radial. What is the distance moved on the sphere of radius r? If theta is changed by d theta, it is r d theta sector on the sphere. Sphere on the plane will become circle. R d theta a theta plus, keeping theta and phi constant, I am there on a circle of radius r sin theta. If I vary phi by d phi on a circle of radius r sin theta, I will move a distance of r sin theta d phi, theta and phi in radian, to produce a phi component. This is dl bar. Please check it. If I change r, I am just moving away from the origin, because of which it is the distance only. Change it by dr. Keeping r and phi constant, if I change theta, I am moving on the sphere of radius r along a circular path on it of radius r through an angle d theta, because of which in theta direction I will move through r d theta. Next, once I fix r radius of the sphere as r and semi-vertical angle of the cone as theta, I am there in a circular path of radius r sin theta. On this circular path, I have to change phi. Whenever I change phi, I am moving on that circle. If I change it by d phi, I will move through a distance of r sin theta d phi, because of which the differential vector in this coordinate system at any point r theta phi is dr, ar, r d theta a theta, r sin theta d phi, r sin theta d phi a phi. What is the differential length? I'm not worried about it. Normally we will not use anywhere. But differential length dl is equal to what? At any point is dr squared plus r squared d theta squared plus r squared sin squared theta d phi squared. At any r theta phi. This is the differential length dl. Since, please check it, dl r bar is what? On the sphere of constant radius r, I cannot change r. I can only change theta and phi, because of which the vector is r d theta a theta plus r sin theta d phi a phi. These are the two components that I can produce on the sphere of radius fixed r. R is r not here. Because of which differential surface element on sphere of radius r is what? R squared. Very, very important. R squared sin theta d theta d phi. Correct? R d theta into r sin theta d phi. This is so important for us, because ultimately people talk about this as differential solid angle d omega sin theta d theta d phi. R squared d omega is the cap-like surface area, which is the part of a sphere of radius r. DSR is r squared sin theta d phi. If I want to determine the area of a sphere of radius a, it is integral of ds a, which is equal to what? Double integral of a squared sin theta d phi, sphere because of which it is theta is equal to 0 to pi, phi is equal to 0 to 2 pi total sphere. What is this? A square comes out. Then sin theta d theta from 0 to pi is what? Minus cos theta from 0 to pi is 2, correct? Integral 0 to 2 pi d phi is what? 2 pi. Because of which this surface area of sphere of radius r is 4 pi a squared. dsr. Very important differential surface and the surface in spherical coordinate systems is this only. The other things are of just know with mathematical interest. I look at them as what? ds theta. dl theta bar is what? If my semi-vertical length, the cone is fixed at any point, I can only vary r and phi on the cone. Because of which it is dr ar, no theta component, plus r sin theta d phi a phi. Theta is fixed. Of course, whenever I say the dl theta, I would have fixed the theta. I will not have any confusion there. The theta is theta naught. Hey, dsr bar is what? If it is bar plus or minus ar. Now, ds theta is equal to one side is dr, another perpendicular side is r sin theta d phi, because of which ds theta is r sin theta dr d phi. In this, r only can change. R and phi only can change. Theta is constant at theta naught, given theta naught for this cone. And what is this bar? Plus or minus a theta. Into the cone is minus a theta, out of the cone is plus a theta. Through the surface. ds theta bar. Next, dl phi bar is, I can only change r by dr, theta by d theta, a theta. Because of which the differential surface element on phi is equal to constant plane ds phi is equal to r dr d theta inside the sphere ds phi. What is ds phi bar? Plus or minus a. These are the various differential surface elements that we use standard in the spherical coordinate system. And finally, differential volume cannot be a vector, is equal to what? dr product of dr r sin theta, sorry, r d theta is another side. Another side is r sin theta d phi, because of which dv is r squared sin theta dr d theta d phi is the differential volume element. Anyway, you can see that sin theta has no units, theta phi dimensionless quantities, right? R squared dr is meter squared into meter, because of which differential volume should always be meter cubed. Differential surface everywhere r dr is meter squared. R sin theta dr is meter squared. R squared sin theta d phi is R squared is meter squared, because of which every differential surface element should have the units of meter squared. Every differential volume should have the units of meter cubed. If you want to know, if I want to calculate the volume of the sphere of radius A, volume of the sphere of radius A, volume, every point inside that volume I want to talk about. Integral 0 to A R squared dr, remaining things are constants. Next, integral 0 to pi sin theta d theta. Next, integral 0 to 2 pi d phi. The first integral gives me a cubed by 3. Integral sin theta d theta, we saw just now, from 0 to pi is minus cos theta, from 0 to pi is 2. Integral d phi from 0 to pi is 2 pi, because of which the volume of the sphere of radius R is equal to what? 4 by 3. Radius A is 4 by 3 pi a cubed. Please check it. These are all the things that I will be using in the topics to come. Oh, this all okay. This is about spherical coordinate system. Check it. I want you to see all these things sincerely. Tomorrow, I'll not take the class because so much you have to look into. But by tomorrow evening, I will send you a list of problems to be done. Integration. Tomorrow you will do them. Understanding things from what we discussed this weekend. Monday, tomorrow we will not have class. Okay. Tuesday we will again have. And that Tuesday we'll be looking at the problems that I have sent on Monday. Wednesday we'll talk about the fundamentals of fields. I'll go to Coulomb's law, all those things I will talk about. Okay, one part. Many problems I'll send, right? As many problems that I can collect. I'll send them tomorrow by evening. Do them tomorrow by yourself, right? Look at the integrations required for that, and then have the method to actually derive the standard integrals also if it is required. We'll meet on Tuesday. These are the coordinate systems. And this is the extent to which we are supposed to know about these coordinate systems. Normally, there are formulae where we convert the spherical vector into Cartesian vector and Cartesian to spherical. They are all very typically, now I don't use anywhere. Is there? I'll send you the material for the three-dimensional coordinate systems. Just see them. No issues. Tomorrow, tonight only, we will get that material. Maybe if it is there with me. Otherwise, tomorrow morning, I'll send the three-dimensional coordinate systems material as such. I think I've sent. We'll see. Otherwise also I will send all the three coordinate systems: Cartesian, cylindrical, and spherical coordinate systems. Just notes is there, small material like notes is there. Just look into that. Then we will go into the single, double, and triple integrals corresponding to the mensuration, where length of the curve, area of the surface, standard, and then volumes, standard volumes may be the first set of problems. Simultaneously attacking all the three, single, double, and triple integrals.